As the Artemis II crew, Wiseman, Glover, Koch, and Hansen cross the translunar injection point today, April 2nd, 2026, the world is watching the most expensive engineering feat of the decade. The Space Launch System, or SLS, is a triumph of safety, but it carries a staggering price tag of over $4 billion per launch. To understand why NASA is still using this expendable economic model while SpaceX just set a record with a 34th flight of a single Falcon 9 booster, we have to look back. We have to look at the $209 billion lesson that started it all, the Space Shuttle. This is the ground truth of how we reached the moon and the hidden math that almost broke the industry. In 1972, NASA promised Congress the Space Shuttle would cost $118 per pound to reach orbit. The actual number came in at $27,000 per pound, a cost overrun of 230 times what legislators had been told. The Space Shuttle program consumed between $192 and $209 billion across 135 missions from 1981 to 2011. Every launch cost approximately $1.5 billion. The reusable spacecraft that was supposed to make orbit affordable became the most expensive way to reach space ever built. This matters because everything America depends on in orbit, GPS navigation, weather forecasting, secure communications, financial transaction timing, requires getting hardware off this planet. For decades, that capability came at extraordinary cost. The story of how the economics transformed and what it means that a single company now conducts more than half of all orbital launches on Earth begins with understanding what the shuttle program actually revealed. The shuttle wasn't a failure of engineering. The shuttle was a vehicle that could carry 27,500 kilograms to low Earth orbit, bring cargo home, and fly again. NASA pioneered reusability concepts that aerospace engineers would study for decades. What the shuttle program demonstrated was that reusability alone doesn't reduce costs. The entire operational model has to transform. The Saturn V rocket, fully expendable and thrown away after every flight, had delivered payload to orbit in the Apollo era for roughly $5,000 per kilogram. The reusable space shuttle delivered the same payload for $54,500 per kilogram, 11 times the expendable price. The economics pointed to something beyond the vehicle itself. The space shuttle's thermal protection system required 35,000 individual heat tiles, each one manufactured for a specific position on the orbiter, each one requiring individual inspection after every flight. The main engines came out after every mission for meticulous overhaul. The solid rocket boosters splashed into the ocean and had to be fished out, disassembled, inspected, refurbished, and reassembled. The workforce numbers reveal where shuttle economics actually broke down. A single space shuttle launch required approximately 12,000 people. A comparable Delta rocket launch required around 1,200. That 10-to-1 ratio in human labor represented the operational model the shuttle program couldn't escape. NASA Administrator Michael Griffin acknowledged in 2007 that the shuttle had been designed for cost-effectiveness at a weekly flight rate. And this goal was never credible. The maximum annual flight rate the shuttle ever achieved was 9 missions in 1985. The lifetime average settled at 4.5 per year. Vandenberg Air Force Base provides the starkest illustration. The Air Force spent over $4 billion constructing a complete duplicate shuttle launch complex in California. After the Challenger disaster in 1986, that entire facility was dismantled. Vandenberg's shuttle complex produced exactly 0 flights from a $4 billion investment. When the shuttle retired in 2011, the American launch industry it left behind had settled into expensive equilibrium. A joint venture between Boeing and Lockheed Martin held effective monopoly over government launches. The government paid this provider over $800 million annually for something called launch capability maintenance. That $800 million covered workforce retention, facility upkeep, and standing capability to launch on demand, all before a single rocket left the ground. When launch rates decline, these irreducible fixed costs spread across fewer missions, driving unit costs higher, which reduces demand further. The Titan rocket family traced this death spiral across 4 decades. $14 million per launch in 1964 became $432 million by 1999 as the pad designed for 24 annual launches eventually supported just one. Here's the insight that finally made reusability economics work, and the shuttle program helped prove it indirectly. Propellant costs almost nothing. Propellant for a Falcon 9 launch runs roughly $200,000 to $300,000, less than half of 1% of what customers pay. The fuel that pushes a rocket off the planet represents a rounding error in launch economics. The first stage booster accounts for 60 to 70% of hardware costs, somewhere around $30 to $40 million. Throw it away every time and that cost hits every mission. Fly it 30 times and the amortized cost drops to roughly $1 million per flight. The operational model had to become fundamentally different from the shuttles. Minimal refurbishment between flights, rapid turnaround, standardized production. What made minimal refurbishment achievable was designing the booster from the start for reuse, rather than adapting a system originally conceived as expendable. The grid fins that steer the booster during descent, the landing legs, the reinforced structure, all of these were integrated into the original architecture rather than retrofitted. NASA's Commercial Orbital Transportation Services program, which invested $800 million total, with $396 million going to one primary contractor, produced something traditional aerospace contracting hadn't achieved. NASA's own analysis found that developing the Falcon 9 cost approximately $443 million. Traditional cost-plus government contracting would have produced an estimated $1.38 billion for the same rocket, a 68% cost difference for identical capability. The commercial list price for a Falcon 9 launch now sits just under $70 million. Internal cost estimates run between $20 and $30 million per launch, with booster refurbishment estimated at just $250,000, a figure that surprised even industry analysts who expected an order of magnitude higher. European industry analysts independently modeled profit margins of 50 to 70% on every commercial flight. High flight rate compounds these economics in ways that aren't immediately obvious. Rapid turnaround means the same booster generates revenue multiple times per year rather than sitting in refurbishment for months. Manufacturing lines stay active, retaining skilled workers and institutional knowledge. Problems surface quickly through flight data rather than sitting undiscovered between infrequent missions. The reusability statistics now read like this: 592 successful booster landings out of 605 attempts produces a 97.8% success rate. One Falcon 9 booster, designated B1067, has now flown a record-breaking 34 times, hitting that milestone on March 30th, 2026. In 2025, SpaceX conducted 170 successful launches, accounting for nearly 86% of all U.S. orbital activity. While the Artemis II mission currently in flight relies on the $4 billion expendable SLS architecture, other nations are pursuing different affordability strategies. India's Chandrayaan-3 achieved a lunar landing for just $74 million total, less than the production budget of the Hollywood film Gravity. By leveraging labor costs roughly 1/8 of American rates and institutional frugality embedded across decades of constrained budgets. Europe's Ariane 6 took the opposite path, consuming €3.8 billion in development compared to roughly $300 million for the Falcon 9, a 13-to-1 ratio that now requires €340 million annually in government subsidies. China conducted 92 orbital missions in 2025 with competitive Long March pricing around $15 million, but export controls bar any satellite with American components from Chinese rockets. Each approach reveals something about what actually drives costs down: operational tempo, workforce efficiency, and the compounding returns of reusing hardware that works. The cost trajectory spans 45 years. $54,500 per kilogram on the Space Shuttle, $2,700 per kilogram on the Falcon 9. potentially under $300 per kilogram on the next generation of fully reusable vehicles. Citigroup modeled a best case of around $30 per kilogram by 2040 and a bear case of $300, calling aspirational $10 targets more of an aspirational goal requiring significant improvements in materials design, propulsion technology, and operating costs. Direction tends to prove correct, while timelines run optimistic. The implications are already measurable. The global space economy reached $415 billion in 2024. Commercial launch services alone generated $9.3 billion, up 30% from the previous year. Active satellites in orbit tripled from roughly 3,400 in 2020 to over 11,500 by the end of 2024. One constellation alone now exceeds 9,000 satellites, serving over 8 million subscribers, a business model that simply doesn't close economically at historical launch prices. Companies are already building toward cost structures that don't yet exist. Orbital refueling ventures are constructing what amount to gas stations in space. Pharmaceutical manufacturing in microgravity is moving from research to production. These applications require not just affordable launch, but predictable, frequent, reliable launch. The kind of infrastructure economics that only emerges when reaching orbit becomes routine rather than exceptional. But concentration of capability raises questions worth examining. One investment bank observed that having such a dominant launch provider is probably not healthy in general for the commercial prospects of the industry, because no one wants a monopoly choking out one point of the value chain. The risk isn't theoretical. An upper stage failure in July 2024 temporarily grounded Falcon 9 operations. A Space Force official put the concern directly. If a mishap grounds Falcon 9, the fleet stops flying, which means the country could lose launch capability entirely. When one provider conducts more than half of all launches worldwide, conducts all crewed American flights to the International Space Station, and carries nearly 90% of global mass to orbit, that provider becomes critical infrastructure in ways that transcend commercial competition. Blue Origin successfully landing its New Glenn booster in November 2025 and Rocket Lab's Neutron expected in 2026 represent more than market competition. Blue Origin and Rocket Lab represent systemic resilience for a capability that nations, militaries, and the global economy now depend on. The billion-dollar ride became a million-dollar ride in one generation. What the Space Shuttle program's $209 billion investment ultimately proved was that reusability requires more than reusable hardware. The shuttle program proved that reaching orbit affordably requires transforming the entire operational model, from workforce to turnaround time to refurbishment scope to flight rate. That lesson cost decades and billions to learn. The economics that followed changed what's possible in orbit forever.